Okay, you've heard about the first derivative test now. Now you have another option, the second derivative test, which is very similar. So the first derivative test, we asked ourselves, what can we say about the first derivative at a local minimum and a local maximum? We're going to start this one the same way. If I have a local, whoa, if I have a local maximum, what can we say about the second derivative? If I have a local minimum, what can we say about the second derivative? All right. So the idea is first derivative has to do with increasing or decreasing. If you have a positive first derivative, the function is increasing. If you have a negative first derivative, the function is decreasing. Remember, second derivative is concavity. Okay. So if we have a local maximum, this is concave down. Whoa. If we have a local minimum over here, that's concave up. So we're going to find critical points again, but this time we'll look at the second derivative to decide whether it's concave up or concave down, because if it's concave up, it has to be a local min. If it's concave down, it has to be a local maximum. All right. And that's what we're going to bring us to here. On the next page, the second derivative test. So again, it's going to start off the same way. If the point A comma f of A is a critical point, this time we have 3 cases. Even more fun, right? So if the second derivative is positive, that's concave up. It looks like this. Then this is a local minimum. If the second derivative is negative, right, then it's concave down. And that's going to be a local maximum, right? Going to be local max. Finally, third case, if the concavity, if the second derivative is 0, no conclusion. Could be either, could be neither. So this is the sad situation. Is if the second derivative is 0, we actually can't use this test, and we have to go use the first derivative test. All right, so don't really want that. But we can look at concavity. We can either look at, are we going from increasing to decreasing? That's first derivative test. Or we can say, are we concave up or concave down? That's a second derivative test. Let's get cracking with this. Example 2. Find local extrema. And then it gets better. And sketch. All right, so these graphs really don't have to be super pretty. It's just, I'm going to be very clear about what information I want you to find and what information I want you to include in the graph. So here, the only thing I want you to do is use the second derivative test and then show the local extrema. And I specify that for the quiz this week. All right. So this function here will be the function f of x equals 1/9 x cubed minus x squared. So very similar steps to before. When you find the critical points. Next step, we're going to use the second derivative test. So use f double prime and second derivative test. And then we'll sketch. We'll include this information. All right. So we need to find the critical points. Remember, critical points is when the derivative is undefined or equals 0. So we have to find that derivative. Use the power rule here. 1/9 times 3, 1/3, x squared minus 2x. Question is, when does this derivative equal to 0? And the answer is, well, let's write it out. So to solve an equation equal to 0, a quadratic equation, you can either use a quadratic formula or factor. We're going to factor again. We have a greatest common factor of x. We're left with a 1/3 x minus 2. This is going to have 2 solutions, each when each part equals 0. So the first part equals 0 when x is equal to 0. And the second part equals 0. Add 2, multiply by 3 when x is equal to 6. So these are the x coordinates of our critical points. X values of, hey, behave, our critical points. Next, we need to find the y values. So, because again, critical points are points, believe it or not. We need to find the y values of these critical points, and then we'll classify them with the second derivative test. So 0 and 6, let's find these y values. So the function, when x is equal to 0, is 0 cubed minus 0 is 0. And the function value at the other location of the critical point, when x is equal to 6, we'll have 6 cubed over 9. Yeah, I got to use a calculator on this one. 6 cubed divided by 9 minus 6 squared, which is negative 12. So we have our two critical points. Critical points are 0, 0, and 6, negative 12. And again, be very careful when you're plugging in, when you're looking for y values, you plug it into the function. It's the function that gives you the y value. It's the derivative that gives you the slope. It's the second derivative that gives you concavity. All right, speaking of the second derivative, we have achieved objective 1. So next, we need to use the second derivative, find the second derivative, and use that second derivative test. So the first derivative, remember, first derivative was, what was it? 1/3 x squared minus 2x. So to find the second derivative, we just take the first derivative again, use the power rule, the 2 comes down. 2 times 1/3 is 2/3. Left the x just there, and minus the derivative of 2x, which is just 2. So this is our second derivative. So we look at the second derivative at each of these points, okay? We'll look at the second derivative when x is equal to 0. That first x coordinate of our critical point. We plug in 0 into the second derivative, we get 0 minus 2, or just negative 2. We have a negative second derivative, which means that our critical point locally looks like this. Is that a local max or a local min? It's something concave down because it has a negative second derivative. That's going to be a local maximum. So this first one right here is going to be a local max. And we'll do the same thing for the other point. We'll look at the second derivative at the other critical point. We'll plug in 6 into this second derivative function. 2/3 of 6 is 4. 4 minus 2 is 2. Second derivative is positive 2, which means it's going to be concave up. And again, concave up, what kind of minimum or maximum is that? It's a minimum. We're at the bottom of a hill if it's concave up. The second one will be a local minimum. And don't celebrate just yet, because remember example 2 asked us to find the local extrema and sketch. So we have found the local extrema right here. That part's done. Now we need to include this information in a graph. Okay, so if we do that, we're gonna get drawing on a graph over here. Ooh, almost jumped up there. We have big x values and big y values. So we'll count by 2 over here, maybe 2, 4, 6, 8, 10. Wait, 2, 4, 6, 8, 10, 12. We'll count by, you can count by whatever you want, right? You just have to include it in the information. So for the y, we'll count by 1 in the x coordinate direction. So this is 5. That's negative 5. And then we do have to get down to negative 12. So I'll count by 3. Why not? That'll be negative 6. That'll be negative 12. Again, you can count by whatever amount you want. Just make sure to label it. We have these local extrema over here. We need to plot these local extrema. So plot the point 0, 0 and 6 comma negative 12. 0, 0 is right here. X equals 6 is here. And we have the y value of negative 12. Now we've plotted the points, which is good. We need to incorporate the information now, right? That 0, 0, that was a local maximum. So around here, the local max. We don't know the big picture, but locally, that's what it looks like. 6 comma negative 12, this other one, is a local minimum. We don't know the big picture, but locally, it looks kind of like that. And now this is a cubic function, so we just kind of connect the dots. All right. Over here, this shoots up. Presumably, they kind of connect some way. I'm going to erase a little bit of this. Oh, my word, that eraser is too big. I'm going to try to connect these ones a little bit more smoothly than what I started with. And then it also goes off this way. So that's an ugly graph, right? Look at this weird little bend here. But that doesn't matter. What I want is, can you include this information that we have a local maximum here, that we have a local minimum here? That's what I want you to sketch here. All right. We'll be doing a little bit more sketching in the next video as well. So we've incorporated all our information. We've plotted our graph. You want to do some more plotting, the next video is the one for you. All right. Good luck.